Hello. Once again, we are back to the continuation of Part 4, Solutions to Stoichiometry Part 4. We had a break for a few minutes and now we continue with the same titration experiment. Before that, let me remind you that there is another way to express the concentration, that is in grams per liter. If it is moles per liter, molarity. If it is gram equivalents per liter, or say only equivalents per liter, it is normality. If it is only grams per liter, it is grams per liter. So in some numericals, you will find the solution concentration in grams per liter. In that case, grams per liter is equal to normality into equivalent mass, or molarity into molecular mass. If molarity is known, then if you multiply by its molecular mass, it gives the strength in grams per liter. Or if you are given normality, you multiply with equivalent mass to get its strength in grams per liter. For example, if the normality of a certain sulfuric acid is 0.5 N, what is its strength in grams per liter? Simply 0.5 into its equivalent mass. Equivalent mass, the N factor as an acid is 2, so 49. 0.5 into 49, 24.5 grams per liter is the strength of the same sulfuric acid, having normality 0.5 N. So let's take up a problem on titration. V1N1 is equal to V2N2. That is the slogan in titration experiment. The equivalents are same. Number of equivalents are same. 20 milliliters of certain solution of NaOH on titration against this solution of sulfuric acid gave 23.6 milliliter of the acid as titer value. So this is from the burette readings. The burette readings, right? And 20 ml is the fixed volume that was taken with the help of a pipette as an analyte solution in a conical flask. This is already a standard solution of sulfuric acid. So it's been already standardized. Concentration is known. I told you, standard solution means whose concentration is accurately known. If it is not known, it has to be standardized. And simply 23.6 into X is equal to, now the concentration, the normality of the base is given. So 20 into 1.01, 1 into 1 by 10. So we get X is equal to V1N1 is equal to V2N2. We get the normality of sulfuric acid is 0.0856 N, or you can write in the same style the way it has given the normality of sulfuric acid. In the same style you can write, or it is 0.856 into N by 10. Right? Now another one. 25 ml of sodium carbonate solution having the strength in 5.3 grams per liter. We just discussed how to convert grams per liter into normality and vice versa, we know. So sodium carbonate solution, as I shall tell you after a bit, is a standard solution. You can prepare an accurately accurate normality of sodium carbonate solution by weighing method. We shall see just after a bit. So 25 ml solution was drawn with the help of a pipette. The concentration is known and it required 27.1 ml, the titer value. This is the titer value of certain sulfuric acid solution. In the previous case, our sulfuric acid solution was already known, standard, but here it has to be standardized by using a standard sodium carbonate solution. And it took 27.1 ml of certain sulfuric acid for complete neutralization in a titration experiment. What is the normality and molarity of the acid? First, let us go for B1N1. First, let us find out what is the normality of sodium carbonate. Strength in grams per liter is equal to strength in grams per liter is equal to normality into equivalent mass. So normality is equal to grams per liter, strength in grams per liter by equivalent mass. So this is 5.3 and equivalent mass of sodium carbonate is 53. The N factor is 2. The total positive charge or negative charge is 2. So 106 by 253. So 5.3 by 53 is 0.1 N. So then V1N1 is equal to V2 into 25 into 0.1 is equal to 27.1 into X. So the normality of the sulfuric acid solution is 0.09225 N. Got it? So it's very simple to find out the unknown normality of a solution if you apply the titration experiment. V1N1 is equal to V2N2. Now, what is called standardization of solutions? I have already told you to determine the normality or the concentration of a solution accurately before the experiment, before you take it to use in a different experiment or in some analysis, you have to first know the concentration of your reagents accurately. So weighing method, this may read out, focus on here while I am reading, focus. Weighing method is in many cases fails to prepare a solution of exact concentration or exact normality or molarity, because the pure substance is unstable. Sometimes it reacts with the components of the atmosphere like nitrogen and oxygen, or it is volatile. By the time you weigh, a part will be escaped to the atmosphere, is volatile. Or sometimes it is hygroscopic, deliquescent, it absorbs water and dissolves in it, so that the mass that you take in the balance becomes different. It's not reliable. That's why, for example, sodium hydroxide, if you you just take some pellets of sodium hydroxide in a bottle and weigh it in a balance, you will find during the time of balance it will be wet, it will be moist, and it will be very, very defective, and the weight that the mass you take will not be the exact mass of the actual sodium hydroxide present in it. Therefore, such solutions are prepared with approximate concentration. You measure, you calculate the amount needed for preparing a decinormal solution of sodium hydroxide, and whatever quantity of the solid sodium hydroxide is required for a given volume of the solution, you calculate and accordingly take the weight and prepare. But that is not the exact concentration. It will be approximate. Then with the help of a titration experiment using another standard reagent whose normality is already known, determined, you can find out the normality of the one which has given an approximate strength, or whose strength is known on an approximate basis, right? So let me read out. Solution having approximate concentration is first prepared by weighing method. Then its exact concentration is determined by titration method by using a standard solution of another reagent. Now, then what is that standard reagent which you can prepare by weighing method? That means such a substance, such a solute is very stable, doesn't have any property of absorbing water, doesn't show any deliquescence, hygroscopic property, nor is unstable, or it reacts with any component of atmosphere, so it's very stable. Such compounds are called primary standards. Let me read out. Some compounds are stable and we can prepare solutions of these with exact concentrations by weighing method. These are called primary standards. These are called primary standards, right? Now, before I tell you what are the primary standards for acid-base titration and in redox titration, let me tell you standardization of reagents is done, is the solution having approximate concentration is titrated. With the help of titration experiment it is done. At the approximate concentration, that solution is titrated with a primary standard solution till the end point. Then V1N1 is equal to V2N2 is applied to find out the exact normality of the solution. This is called standardization of a solution. For example, to standardize sodium hydroxide solution, standard decinormal solution of succinic acid is used, because succinic acid is a primary standard. You can rely on its mass by weighing method and prepare the solution by weighing method. You can get the exact concentration because succinic acid is highly stable. To standardize an acid solution, for example, this is to standardize a base solution. Use standard succinic acid. But to standardize an acid solution, a primary standard sodium carbonate is used. Sodium carbonate solution is also a primary standard whose solution can be prepared by weighing method accurately. So sodium carbonate solution is used to, or a freshly standardized NaOH. For example, you have already standardized sodium hydroxide solution by using succinic acid. And immediately you use that standardized sodium hydroxide solution to standardize an acid solution, right? So this is where we call it a double titration. That means you are given, say, an acid and you are asked to standardize it. You are asked to standardize, say, sulfuric acid of an approximate strength, say, your examiner says it is approximately n by 10. You standardize it. That means to find the exact concentration. Then what do? You have to first standardize a base, sodium hydroxide. Sodium hydroxide that is available in your laboratory is again not standard. It might be an old solution or it may be a new solution, but as you know, sodium hydroxide is not a primary standard, so it's approximately known. So then your first job is to standardize sodium hydroxide solution by using a real primary acid standard, that is succinic acid standard. So you have to do two experiments. First, to standardize sodium hydroxide solution by using a primary standard. Then after having known the normality of sodium hydroxide, immediately use that sodium hydroxide to titrate the given sulfuric acid solution and then find the normality of sulfuric acid. Got it? So read this problem with me. 25 ml of a solution of oxalic acid. You know, oxalic acid is also a primary standard. It is a sister of succinic acid, the younger sister. Just in the homologous series you will learn in organic chemistry. Don't be scared. It is just the younger sister of succinic acid. So 25 ml of the solution of an oxalic acid containing 4.5 grams of the acid per liter, again grams per liter. You have to convert into normality. Of solution neutralized 32.5 ml of a sodium hydroxide solution. So this is the first titration. Here we will standardize sodium hydroxide solution. Then this alkali, standardized alkali, 25 ml of this standardized alkali is taken, and that requires 20.2 ml of a sulfuric acid solution for complete neutralization. Then calculate this normality, the normality of this sulfuric acid in normality as well as in strength and grams per liter. That is in equivalents per liter and in grams per liter, right? So let us handle the first titration. So V1N1 is equal to V2N2. But first let us find out what is the normality. Since its strength in grams per liter is 4.5 grams per liter and oxalic acid is the molecular mass is 90, the N factor, the basicity is 2, the N factor is 2, so 90 by 2 is 45. So 45 is its equivalent mass. So you know normality is equal to, let me do it again here, normality here is strength in grams per liter by equivalent mass. That means 4.5 by 45 is 0.1 N. So that here I have written directly. So V1N1 is equal to V2N2. 25 into 0.1. The oxalic acid solution has a normality 0.1. I'm sorry. Into 32.5 into X. So you get X is the normality of NaOH solution. So once you know the accurate normality of NaOH, that means NaOH solution has been standardized. Then use the same solution immediately to titrate with the given sulfuric acid. So 25 point, this concentration is just now known. 25 into this is equal to 22.2 into Y. Y is the normality of sulfuric acid. So Y comes to be this. And to convert it into strength in grams per liter, so you just multiply this normality factor with the equivalent mass. That will be given how much? Yes, it's not calculated. You can calculate this that much grams per liter. So I'm avoiding delay. You can do it, right? Now, let me tell you some of the important primary standards for acids, bases in acid-base titration, and some oxidizing agents, reducing agents for redox titrations. For acids, the primary standards can be succinic acid and also oxalic acid to some extent. Potassium hydrogen phthalate, shortly called KHP, potassium hydrogen phthalate. Don't bother about its structure. It's an organic compound. So we are not least interested now to write the structure of organic compounds. So that is simply, potassium hydrogen phthalate and potassium hydrogen iodate. So these are three common primary standards as acids. The primary standards for bases is sodium carbonate or a very huge organic compound, hydroxymethyl aminomethane. Forget about hydroxymethyl aminomethane. That is another primary base standard. Then for redox titration, potassium dichromate is a wet standard. The primary standards are also sometimes called wet standards, right? Potassium dichromate as an oxidant, sodium oxalate as a reductant, potassium bromate also as an oxidant, right? So calculated quantity of the solid, that is the primary standard, is weighed accurately in a digital weighing balance and taken in a measuring flask, and slowly distilled water is added with constant swirling motion for dissolution till the volume is made up to the mark. Not that you add, say the measuring flask is 200 ml, you just take 200 ml of water in another measuring device and put it on the measuring flask. It's not that. You have to add water, distilled water, swirling motion, so that it will homogenize, and finally the volume of this solution means the volume of the solvent and solute, because solute will consume some volume, maybe small for dilute solution, but it will consume some volume. In a solid solute, it will consume less volume, but liquid solute, it will consume almost the same volume as the pure liquid component, right? Therefore, you have to make the solution up to the mark. Solution volume should be the one stipulated according to the mark of the measuring flask. So then the stopper is closed after making up to the mark with the help of distilled water. Then you use the stopper, close the bottle, and then shake thoroughly so that it will be completely homogenized. Then you can put a sticker, 0.1 N or 0.25 N or 0.01 N, whatever you put a sticker. Usually decinormal solution is prepared. So N by 10 or 0.1 N, you can write down mark. So supposing you have a 500 ml measuring flask, here is the mark. And here I have copy pasted from from Google source. Here the solute is cobalt chloride dihydrate. So it is a blue colored compound and solution is blue. Doesn't matter. So the accurate, supposing 10 gram accurately is weighed here, the solid, and transferred to the flask. And then slowly, this is empty flask, then it is transferred and slowly it is to be dissolved in ethanol. It's not an aqueous solution, it is an alcoholic solution. So the solvent here is ethanol. Rarely in titration experiment you come across with non-aqueous solvents like ethanol. But this is just an explanation. Then slowly add the solvent, say water, distilled water, and periodically give a swirling motion for homogenization, and then slowly add more and more solvent till you bring the level up to the mark. Then put the stopper, shake it thoroughly well, and then you put a sticker, 0.1 N or 0.2 N, whatever. All right. Now let's take some problems again in the titration experiment. B1N1, B2N2 once again. Particularly, this is a dilution of a solution, a concentrated solution, to prepare a dilute solution. Just read out with me. 5 ml of a concentrated 18 molar sulfuric acid is highly concentrated, is a concentrated sulfuric acid, was diluted by distilled water using a 250 milliliters measuring flask. That means the total volume will be 250. The volume of the solution was made up to the mark. What is the normality of the acid in the diluted solution? Now, when there is no reaction, nothing, then the amount of the solute will never change. However dilution you may make or how much concentration, of course you can't make a diluted solution more concentrated in a real experiment. You have to, you vaporize some solvent for that. But you can dilute 10 times dilution, you can make 50 times dilution, whatever you want. So what will be, when will you dilute a solution, then the amount will not change. So the number of moles will remain the same or the number of equivalents will remain the same. So you can use the principle V1N1 is equal to V2N2 or V1M1 is equal to V2M2 that I have written at the bottom first. You can, because the number of moles or the number of equivalents will be the same before dilution, that is in the concentrated solution, and after dilution, that is in the diluted solution, it will remain the same. So let's read out. 5 ml, small little 5 ml of this concentrated solution was diluted using 250 ml. So this is the final volume. So 250 into the normality of the diluted solution is equal to 18 into 5. 18 into 5 is 90. The number of moles will remain the same, number of equivalents will remain the same, doesn't matter. So 250 into x is equal to 5 into 18, that is 90. This is many millimoles because this is in milliliter, this is millimoles, 90. So here we get x as 0.36 m. So the molarity of the final diluted solution having volume 250 ml, that is the volume of the measuring flask up to the mark, the molarity is 0.36 m. Or you can do it by milliequivalents. Now 250 into y is the normality of the resulting solution, is equal to, the number of milliequivalents, since the n factor, the molarity is 18m, the n factor is 2, so the normality is 18 into 2, 36. So V1N1, 5 into 36 is equal to 250 into y. So the normality you are getting 0.72. And from here you can convert it to molarity. Just divide by the n factor with the normality, you get the molarity. So 0.72 by 2 is 0.36, which we have already determined from V1M1 is equal to V2M2 study analysis. So remember, in dilution problem, you can use V1M1 is equal to V2M2. But in reaction stoichiometry, when you're performing a titration, it's never, ever V1M1, V2M2. They may not be same in most of the cases, but V1N1 is equal to V2N2 is always the case for, because the number of equivalents remain the same. And you know the slogan, the famous song that we sang long ago, that all chemical reactions take place in equivalence. Now, this is another problem that we missed out, is 0.45 gram of oxalic acid was given to you along with a 100 ml measuring flask and distilled water, of course. What will be the normality and molarity of the 100 ml solution that you prepare with this amount of oxalic acid? Now, let's find out, calculate the normality, because normality is the number of equivalents per liter, or number of equivalents by the volume of solution in milliliter into 1000. So 0.45 by the equivalent mass you already know is 45, 90 by 2. So 0.45 by 45 by the volume in milliliters into 1000, we are getting the normality of the 100 ml solution is 0.1 n. It is a deci normal oxalic acid. And since the n factor is 2 here, whether it is an acid 2 or if it is a reductant, then the total change in oxidation number also is 2. So luckily, oxalic acid is not only a dibasic acid having n factor 2, but also as a reductant where the number of electrons lost is 2 for molecule or per oxalate ion. So the molarity is 0.1 by 2, 0.05 m. Right? So another example where we will be using the W by W percent, mass percent. How much? 98% sulfuric acid by mass. It should be by mass because we have a practice of writing by weight. Weight for a layman's purpose is same as mass, but for you it's not the same. But we have a habit of saying weight for mass. Doesn't matter. Once you understand the real implications, the real underlying meaning, so don't be critical about it. So 98% sulfuric acid by mass required to prepare n by 10 solution of sulfuric acid by using a 100 milliliter measuring flask. Right? So let's see how much milliequivalents will be there in 100 ml of n by 10. So volume into normality will be the number of milliequivalents, MEQ. So you can convert it into mass. So 10 divided by 1000, because milli has to be killed. I told you several times, if you want to kill milli, then you have to divide by 1000 or multiply by 10 to the power minus 3. And this is the number of equivalents into equivalent mass, 49 for sulfuric acid. So that comes to 0.49 gram. So once we know the mass of sulfuric acid present, that is also present initially in the concentrated solution. So if it is a 98% sulfuric acid, so if the mass of the solution that we have to take from the stock is X, so 98X by 100, 98% of X is the pure sulfuric acid, which is 0.49 we require. So then X is 0.5 gram. So if you take only 0.5 gram of this concentrated solution and add water till 100 milliliter mark, second, that will be called N by 10 solution of, or a decinormal solution of sulfuric acid. Got it? How is this going? How you are catching? Good? Good. Now, I told you that dilution related problems, often a concentrated solution is diluted before titration. Often, whenever you are going to perform a titration experiment with a burette and a pipette, you have to first see that the solutions are diluted, not concentrated. It is not worthwhile or advisable to use a concentrated solution for titration, because one drop of a concentrated solution will overshoot the endpoint to a large extent. So the normality that you get will be erroneous. So to get a correct, more or less a correct data, normality data, it is always better to use a diluted solution, usually a decinormal solution, approximately decinormal. You can standardize it to know the exact solution strength, right? So let me read out, you just follow me. Often a concentrated solution is diluted before titration. This is because the concentrations of both the reactants should be comparable. Titration of a more concentrated solution, say A, let us take A as titrant, with a less concentrated solution B, say analyte, will give erroneous endpoint result, as the extra one drop of A, which is more concentrated at the endpoint, will produce excess of the unreacted ions by overshooting the true endpoint, and hence the titer value gives incorrect concentration on calculation, B1N1, V2N2. Therefore, the two solutions should be dilute, and also the two solutions have comparable, not exactly identical, comparable concentration. Say if it is 1 N by 10, say 1.05 1 by 10, it can be 0.9, 0.8 N by 10. So they should be comparable. Then only the titer value will be giving you a more or less accurate concentration normality. On dilution, the amount of solute remains the same. So you can use either V1M1, V2M2 or V1N1, V2N2 to find the new molarity or new normality. Note that during reaction, we cannot apply, during a reaction, a titration experiment, we cannot apply V1M1 is equal to V2M2. I have told you several times. Now let's take up this problem. We are at the end of our program. This program is going to end soon. Will I show you so that you will be happy? Yes, it comes after that assignments, right? You are given a 150 ml sulfuric acid solution, right? Whose normality you have to determine. You are asked to determine the normality of a 150 ml sulfuric acid solution. You will be asked to dilute the solution. Before titration, you will be asked, supposing this is a concentrated solution, you will be asked to dilute the solution by using a 500 ml measuring flask to 500 ml by adding the required amount of distilled water. Then you shall be performing the titration experiment. 25 ml of this stock solution, this is called the stock solution. Whatever measuring flask you take to prepare the dilute solution, that is to be branded as stock solution. From there, you take again and again and repeat the titration experiment till you get the same value. And that is called concordant readings. In olden literature, you find when the three readings are same, the differences, final burette reading minus initial burette reading, that titer value is to be exactly identical at least for 3 times. Then only you will be sure that that is the actual titer value. Otherwise, they are all rough, approximate. So these 3 identical values are sometimes called concordant readings, right? Now then you take 25 ml of this diluted solution from the stock and perform titration, and it needed 27.7 ml from the burette readings. You learn that this milliliters of 1.01 n by 10, which has been already standardized before, of a sodium hydroxide solution for complete neutralization. What was the normality and molarity of the original acid solution, right? So again, this is a double titration problem. And I took this problem only to show that there has been a dilution. Before titration, there has been a dilution. So let us first start from the bottom. Let us find out what is the normality of the diluted stock solution. So 27 into 1.01 by 10 is equal to 25 into x. So the x comes 0.1119 n. Right? So this is the normality of the entire stock. Remember, this is not the concentration of only the 25 ml that you have drawn by using a pipette. It is the concentration of the entire stock solution. For example, I used to say this funny example while I teach this. I am now telling this to all of you, and this that supposing you go to a seashore, and brave through the water, take a bath, or you may just drench your feet with sea water, with its waves. And supposing you take some water in your hand and test it. It will be too, salty, because it contains a large amount of salt. The concentration of salt, sodium chloride, is very, very large. So you will be getting a very, very salty test. Very, very salty. Now, supposing you bring, say, 10 ml or say 100 ml of water from the seashore in a bottle to your home, back home, and test a small part, maybe 1 drop, put it on your tongue. Will it not be testing the same concentration, or the salty concentration, or the salty feeling that you were having while you were plunged into the sea is same as with 1 drop of the same seawater? Because if the seawater is same, irrespective of whether you take 20 ml or a drop, the concentration is not going to change. Concentration is the proportion of the solute with solvent, or solute present in the solution, or solvent solute proportion, relative proportion. Therefore, whatever you get in the titration experiment using only 25 ml, because that's why we make a huge stock, because we have to perform several times, repeat the experiment. So whatever titer value, final titer value you get, and whatever concentration we got will be the concentration of the entire stock. So that 500, now initially we had a concentrated solution whose normality is not known. So 150 into the normality of that concentrated solution is equal to, now the diluted solution is 500 and its normality has been found by experiment, by titration experiment. So you get what is the normality of the original solution, 150 ml solution. You are getting 0.373 N. You have diluted to 0.1119 N. So then you take and therefore you took 25 ml each time to perform the titration. And this is the concordant reading, the final identical reading in all three experiments at least, that you got, and got the titer value, and you therefore got the normality as 0.1119 N. And once you find the normality of the original solution, concentrated solution, you can also find its molarity. The N factor is 2 here, so divided by 2, that is 0.1865 M, because the N factor is 2. Boys and girls, ladies and gentlemen, you have watched this particular Solutions Stoichiometry Part 4 in 2 slots, in 2 lectures. And this is, the previous one was about 30-35 minutes, and this is about the same, duration. So we close, and in the next video we will have fascinating last part of our solutions stoichiometry problem, volumetric analysis, that is tackling problems. This is just titration experiment, V1N1, V2N2, and dilution. But how to use these titration in solving so many types of problems, analytical problems, sample analysis involving multiple successive reactions, ending with a titration that sometimes we call the back titration. All these details, its application will be done in our last program. So until then, goodbye, and again the same monotonous exercise. Have you subscribed to my channel, SST Chemistry? Yes? Good. If not, please, can I not request you to do that? And if you like this program, why are you hesitating just to spend a bit of energy to click on the like button? Bye-bye. See you soon.